Hey, Physics 30s. So we're going over the Physics 30 Release Items 2013 edition here. So let's get right at it. Let's not worry about it. I skipped over the answer key. Maybe I should just go get those really quickly so I can double check and see if I'm doing this right. Okay, so I'm back. Okay, so let's get through this. So the first one here, we're just trying to find out what the impulse that's on this car, doesn't specify what kind of car it is, but it doesn't really matter. You just have to remember that impulse, if you're going to calculate impulse, you can calculate it two different ways. You can calculate it going through, remember impulse is change in momentum here. You can get it through, I'm kind of going to say change here. You can go mass times change in velocity, or you can go through force times change in time. You notice that this is a vector, so it does have direction. Doesn't really specify direction in this picture. Let's just assume forwards. And so they want us to find the impulse from 2 to 5 seconds here. So again, we've got some key words here. We're not going from 0 to 5 seconds. We're going from 2 to 5. So it looks like they just want us to find the impulse in this area here. And the reason I'm saying area, because the second formula here, this force times time formula, this is like our width, this is our length. It's like you can see up here, like this is our length here, this is our width. It's like length times width here picture. So if I go length times width on a force time diagram, I'm going to get my impulse. Okay, but we got two parts here. So we've got two problems, or we got a problem. One problem is that there's a triangle. Right? And the other problem are the units here, so the times 10 to the 2. You notice it looks like they did that already, they included those. But that triangle is going to cause a problem. So unless you know the trapezoid formula, 1/2 a plus b times height, which was on the formula sheet at one point, then you might as well just calculate this twice. So this part right here, the first part, that's going to be our length times width. So this is just going to be 20 times 10 to the 2 times the time. So that's just 2 seconds there. All right? And this one, because it's a triangle, it's going to be 1/2 base times height, or length times width. So I have 1/2 the 20 again, that's our height, times the 1 second. All right, so we've got these two calculations here. So the first one, so 2 times that would be 400. I think that's all. It seems like it's too pretty. So not 400, so this is 2,000, so it'd be 4,000. Okay, so I'll just cross off A right now because that's that piece, but we're going to add on an extra piece here. So this piece right here, 1/2 times this number, that's 10 times 1. So this is going to be 1,000 here in seconds. So I'm going to add them together. I'm going to go 5,000 Newton seconds. So I'm going to take those two numbers, I'm going to add them together and get 5,000 Newton seconds. Remember, Newton seconds is the same thing as a kilogram meter per second squared mathematically. And again, I think the units they should have used here were Newton seconds, but whatever. We get that 5,000. So that's 5 times 10 to the 3. Cool. Okay. Next one. Boop, 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 boop. Yeah, so I will print off or save the PDF version of this. It might look a bit weird, but I'll save it because I'm using this program here. It's this car picture again. I don't really want to do this one again. We did this one in a previous video here. Hopefully you got 1.33. I'll just kind of skip past it. Just remember that you can skip this middle piece. It's not needed, all right? Because conservation before and after has to be conserved. So I don't really care about the conservation between what's happening in the middle here. So you can just ignore this whole section, all right? So we just have to find the momentum up here. So this is the momentum before, and then we got the momentum after, right? These just have to be equal to each other. So I can find the momentum of this car, and then use that to help find the momentum of all three cars together. So you do get 1.33. I'll just do it anyway, why not? So this is mass times velocity. So we get 1,500 kilograms here, times its velocity of 4. So we're going to get 6,000 kilogram meters per second. I should probably put the units there too. Okay, so that's the before calculation. Then afterwards, again, it's going to be mass times velocity. But this time the mass is going to be all the cars added together. So we've got the 1,500, we have the 1,200, and then we have the 1,800 kilograms. That's all kilograms there. And we're looking for this. We'll just call that V. So overall, the total mass is 1,500 plus 1,200 plus 1,800. So we have 4,500 kilograms times this velocity that we're trying to find. And what we know about this is that this has to be equal to the 6,000 that's up here. Okay, so we know that this has to end up being 6,000 kilogram meters per second. We have the 4,500 kilograms here, and we're trying to find V. So if I divide over the 4,500, I do get the 1.3 repeating essentially, but 1.33 because we're looking for like 3 sig digs here, meters per second. Cool. So that 6,000 we're using here, right? And then this part of the calculation here is over here. And we know they just have to be equal to each other. Cool. Here we have 2 clay clumps that come in at each other, but not collinear. All right, so they're going to come at different angles to each other. It's technically 90 degrees, it looks like. So hopefully this is a 90 degree. We can probably make that assumption. So this one on the top here is going directly horizontal. So if that's going directly horizontal, if I were to look at its X and Y components, this one is all X, but has 0 Y. And then if I do this one, because it's going vertically, this is all Y, but no X. So we can calculate these momentums. Let's just find those momentums, because we're going to have to create a momentum diagram down here. Okay, we probably don't even have to do too much math to do this after we find out what the numbers are here. We're going to go mass times velocity. So our mass, 2 kilograms, times that 6 meters per second, and we're going to get 12 kilogram meters per second. Okay, so we got the 12 here, kilogram meters per second. We're going to do the same thing with this block over here, mass times velocity. My head's going to get in the way here. Let's write down here. 2 kilograms times the 4 meters per second. And we're going to get 8 here. So this is going to be 8 kilogram meters per second in that spot. Okay, so I know because the two X and Y's are not the same, it's not going to be 45. This angle here is not going to be the same angle. Oh, the same thing. This is not going to be 45 because the two side lengths are different. The top's bigger than the bottom, so it's got to be D. All right, but let's see if we can actually find that 14 and find the angle as well. Might as well. So when we're finding like the total system, this is all before the collision. I know it says this is immediately after, right? After, but before and after are the same, right? Momentum before is equal to the momentum. Oh, my head is in the way. Oop. Is equal to the momentum after. Okay? So if I find the momentum beforehand, I just found the momentum afterwards. So it doesn't really matter which one you find. So we have all the before information here. So the sum of all the momentum, right? The sum of all the x's and the y's, if I add all my x's together, well, it's only one of them, so it's 12 kilogram meters per second. If I add all the y's, that's 8 kilogram meters per second. And if I were to draw out the picture here, let's go x first. So I have 12, and then go 8. And then if I were to draw my vector that we're trying to find here, that's what we're trying to find. And maybe I'll find this angle in here too. Looks like they, oh yeah, so they find it towards the x-axis, toward the y-axis. looks like we're trying to find towards the x-axis. Now to find out what that question mark is, we're just going to use Pythagorean theorem. Like, let's see, r squared, our resultant, is equal to 12 squared plus 8 squared. 12 plus, so that's 12 squared, that's 144 plus 8 squared, 64. That's 208. And then we'll take the square root of that answer. Okay, so this is, what does it say? 208. So r is 14.4. So remember, you got to take the square root of that answer up there. So 14.4 could have crossed off A and B because of just that as well, but the angle there is a bit off. And yeah, we want to find this angle. All right. So to find the angle, we're going to go tan. So I'm going to find, I'll just call this theta here. Remember, tan is going to be opposite over adjacent. So to find the angle, I'm going to go tan inverse 8 over 12. I guess you could reduce that down, but it doesn't really matter. Your calculator does it for you. Just make sure you're in the right mode. So I get 33 point, there's no northeast, southwest in this question. So it's going to be 30, let's say 34 degrees. So this angle here is 34 degrees, right? So it's obviously not this one. That's the wrong angle. So the other angle, if this angle here is 34 degrees, the other angle, which is 90 minus 34, should be 56. Let's double check. Yep, 56. Check mark. That worked out. So everything here works out. Yeah. Perfect. So the answer is D. Cool. Okay. In the exploration of Mars, planet Mars uses a robotic probe because the conditions involved in such a mission are dangerous to humans. Yeah, lots of radiation and stuff. One mission to Mars uses parachutes, brings the lander to safe landing to rest on the planet's surface. Maybe that's going to be important later, the rest. It doesn't look like it. I think I remember this question. The parachute slows the lander's speed and falls to the atmosphere. Airbags are required so the lander reaches the surface, or when it reaches the surface. After a series of bounces, it comes to rest and releases the robotic probe. Okay, so I've got some information about this lander here. It's got a mass of 360 kilograms. The speed is going 600 at the top of the atmosphere, but just before it hits the ground, it's going 18, so it slows down quite a bit there. And then afterwards, it's bouncing upwards. This is the first bounce, right? Yeah, the first bounce. So what's the momentum as it entered the atmosphere? So what's the momentum as it entered the atmosphere? So we're using this one here as it enters the atmosphere, the 600. This one doesn't seem too bad. So my momentum here is going to be mass times velocity. So I know I'm 360 kilograms, and I was going, how much? 600 meters per second, yeah. Yeah, 600 meters per second. Okay. Times those two numbers together, you should get the proper answer here. 216,000 kilogram meters per second. So that's going to be our answer. Is going to be D again. Now, why is the airbag important in this situation? I don't know. Let's read the thing. Okay, so increasing the impulse. No, we don't want to increase the impulse. No, I don't think we want to increase the impulse. Decrease the impulse, maybe. But how would we do that? I don't know. I don't think the impulse is going to change because the bounce before and after the mass is there really is not going to change too much. What it can change is the time it takes, right? Because it's going to create that cushioning effect. It's going to slow down slower, but it's going to get the same speeds overall. So the impulse is probably going to be the same. So I'm just going to write that down here. So impulse is the same either way. I'll write down since mass times change in velocity. This is the same, right? So we're going to cross those ones off, okay? But to get that, because the impulse is going to have to stay the same, So if impulse is going to stay the same, this is going to be constant. What I want to try to do is reduce the force. So if my time goes up, my force has to go down, right? So I want to increase my time. That's the whole cushioning idea, where you want to cushion it and you want to increase the time as much as possible. The impulse here in the first collision. So the impulse, the first collision, we got the before and after speeds. Remember up there I talked about how impulse is mass times change in velocity. So to get that impulse, which is going to be mass, like I said, times change in velocity, I'm going to have to go my mass, which is going to be 360 kilograms, times my final speed minus my initial speed. So I'm going to subtract those two. But now the very key part about this is that there's different directions here, right? It's going down, it's going up. So we have to worry about, because impulse is a vector, we got to worry about direction and sign convention. So if I said like down is negative and up is positive, that's going to be very important for these kind of questions. So my final is going to be a positive number. Oh, where did I go? So my final is going to be positive 11. And I'm going to minus this negative number, this 8, I think it was 18, right? Yeah, minus this negative 18. So I'm minusing a negative. So I'm going from positive 11, where's my hand? Positive 11, all the way across the number line, past 0 to negative 18. So I got to look at that whole change. Right, so it's 11 and the 18 on both sides of this number line. So that's going to be technically a really big change of 29, right? Let me just type in my calculator. And we get 10,440 Newton seconds, right? Because this is impulse. Which is that? That's going to be D. Now, if it had a direction, because it ended up being positive, and I said up was positive, this is upwards. I don't know if it's going to be really, it's not important here. Now, the collision can be classified as probably inelastic. You can look at the calculations here. If you go 1/2 mv squared to these two numbers, because one is bigger than the other, they're definitely not going to be the same thing, because you go v squared 18, v squared 11, definitely not the same number. So kinetic energy is not conserved here, right? So kinetic energy is not conserved. Momentum is always conserved, so we could put that in there. Let's get rid of this one. And kinetic energy is definitely not conserved here. We'll cross off those two. So you have these two options. And because the kinetic energy is not conserved, it's definitely an inelastic collision, right? So I'm just doing, like if I were to do initial energy and the final energy, this is elastic, so you always have to worry about kinetic. Right? 1/2 mv squared, 1/2 mv squared. You do the two calculations here, 1/2, 360. I'm not even going to bother typing them in, but we got 11 or 18 for the initial squared. And then if I do it for the other one, 360, but now we're at 11. Even though it's a negative number, remember this it's a scalar vector and you're squaring the number anyway. You lose that negative. Oh, oops, I put the square on the, I should put it on the inside, or the outside here. So this one's bigger, right? So it's definitely not conserved. Cool. Continuing on, so this, like, if you look back here, this is like for the next 8 questions. So we're going to use, we may have to jump back to those numbers up there, but here's additional information for the next 3 of the questions. And then there might be some additional information after that. All right. Robotic probe has a variety of instruments, including devices that use ground-penetrating radar and spectral spectroscopy. I don't even want to say the word. SPM. Okay. And used to investigate the planet Mars. The ground-penetrating radar can be used to examine the structure, searching for specific rock formations, blah, 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 presence of water. Is an antenna length of 1 meter. That could be useful, which is half of the wavelength of the EMR. So that, I'm going to write down something here that you might need it, because this is half of the wavelength, that's 1 meter, is half the wavelength. So it means the wavelength is actually 2 meters. So I'm going to write that down. I might need that. some information there. Okay, so my wavelength's 2 meters. The SBM can be used to identify the person. Blah, 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 blah. Emits an EMR over a broad spectrum, detecting wavelengths that are reflected, being examined. The photons that are not reflected cause electromagnetic radiation to cause electromagnetic transition within the sample. Okay. The graph below shows a particular sample. And then down on the bottom here, we got some wavelengths of the sample. So you got CO2 here is at 15. And then something over here. I don't know what that one is. At the top, what's CO2 collision there? Okay. So the region of the EMR spectrum in which the ground penetration is classified is times 10 to the negative 6. So if I want to put that in perspective, I may want to change these numbers here. Like this is from like 5. This is like 10. Right? Like 10. So say I would change 10 times 10 to the negative. Oh, just 1 second. I don't know what I'm trying to do. Yes, 2. So that's definitely radar. Oh, it's radio, sorry. Yeah, remember we did that question with the wiggles. It's about the height of a person usually. But if I did it for the 10 here, I don't know what these ones here. These are the reflected EMRs. I could change these as well by dividing by 10 to the negative 9. This ends up being huge. It's like 10,000. 10,000 meters or so. That's definitely a big number. Oh, nanometers. Well beyond visible range here. There we go. Infrared? Probably not. I would go radio on that one. That's what they went with on the answer too. We did a question where radio waves were about approximately the size of a person. It was the Wiggles question. Yeah, maybe. And they get larger, size of mountains and stuff. Microwaves, like we were saying, the size of the holes, can't really see it. The size of the holes inside a microwave. And the infrareds are pretty close to the visible spectrum. As a result of the collision between the photon and the carbon dioxide molecule in the sample, the molecular underwent a transition to a higher energy state, probably, because it absorbed the energy. Okay? And the photon was absorbed. And the photon was absorbed. Between a photon, yeah, so it was being absorbed and it was going to a higher state. All right, so these carbon dioxide molecules are in ground state. A photon comes along, gets absorbed. Those electrons go to a higher state. When it jumps back down, it's going to emit that EMR. Okay? So we can actually probably figure out what that is. I think it says up here. We can find out. It looks like about 15 times 10 to the negative 6 nanometers for that carbon dioxide. So the difference. So we just want the difference between the two states. So if it absorbed 15 times 10 to the negative 6, let's go with that one. Meters. I can convert that now if I want to. I don't need to go back to nanometers for this because we need this in now. I can find the energy by going HC over lambda. Now we're just going to make sure we're using the proper H. I want my answer to be in electron volts here. If I use the wrong H, I'm probably going to get the wrong kind of exponent anyway. So I'm going to use the 4.14 number times 10 to the negative 15 times by the speed of light here. And I'm going to divide it by this wavelength. He knows I don't have to put this all the numbers in proper scientific notation as long as I have the proper the proper times 10 of the stuff in the right spot. Okay, let's see what we have here. Divided by 15 to the negative 6. Okay, so it looks like I get, when I do this, I get 8. Well, my calculator spits out 0.0828, Now they want a scientific notation, so you got to move this over twice. So 8.28 times 10 to the negative 2 electron volts. That's really low energy, so it must be not visible. Yeah, visible is like in the 1s and the 2 electron volts. I think we did some questions like that before. So if I fill this out, I'm going to go 8282. It's kind of a fun number. There we go. Got to just make sure we got the right numbers there. There we go. All right, so the probe, okay, another information about this. The probe was also equipped with a microscope that uses polarized light. This light passes through a mineral sample being analyzed. Certain minerals can be used, can cause the plane of polarization to change. Like glass does that just in your car, polarizes the light. You don't really notice it too much, but it does. The glass in your phone also polarizes light. Glass is a natural polarizer. The light was then passed through a polarized filter and the signal was detected. The 3 arrangements can be shown below. So we got straight up and down, straight up and down, straight up and down, perpendicular to it, kind of like off at a weird angle, and then this one's straight up and down. In order for the arrangement, blah, 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 that would produce the strongest to the weakest. All right, so I want to go for the strongest signal. So if you think about this one here, like the wave, it's going to go through here. The light here is being polarized up and down here. So it's going up and down, up and down. All right, so as it goes up and down, if it comes towards something that's not up and down as well, it's like trying to get something that's going this way through a door that's perpendicular to it. It's just not going to work. So this is going to be my weakest. It's just going to kind of cancel it right out. Right. So my strongest is if it's oriented the same way, right? So if I'm going up and down, up and down, up and down, this can just go right through the door, right? So nothing's going to happen. And this one here is going to go at a weird angle, right? So when it does this, it does orient itself up, but it will be slightly weaker as it goes through there. Because only part of that wave is actually going to get through that little opening there. So our strongest is going to be 1. Okay, so let's cross that off. And my next one would be 3, and my weakest would be 2. So strongest to weakest. All right. Let's just check the answers as they go. Okay, cool. So we've got these electroscopes here. So remember what electroscopes are. They're just like little devices that if you charge them, the 2 plates become the same charge and they either flip away. If they're not charged, they kind of stay neutral to each other, so they just don't do anything. So they can either both be positively charged or negatively charged. They'll just do the same thing. So we got the electroscope 1 touches a neutral metal rod, and student touches the one with a glass rod. Okay, so now they just want to know what happens to each one. So if I take one and I touch the electroscope 1 with a neutral rod, it's going to, these look like they're charged right now. So they're identically charged. So either both negative or both positive. So I don't know which one's which. But they are charged. Let's just assume that they're negative, right? So we've got some negatives on both of these now. So everything's negative. So if I come along with a metal rod, which is a good conductor, if the metal rod touches this, and it happens to be neutral, these electrons are going to distribute themselves further apart. So they're going to start moving around, distribute themselves around this device. And some of them are going to come up here and distribute themselves on top of this metal rod. All right? So it's going to take away some of those negative charges. But if it's a glass rod, so this is metal, glass rod is an insulator. So the electrons are not going to go on to the glass rod. They're just going to stay where they are. So the electrons are not going to move. So glass is an insulator. Insulator, this one over here is a conductor. Okay. So if I touch it with a glass rod, I'm not going to do anything. So So I'm going to cross off the ones that look like they just kind of discharged it, where the electrons moved. But then the other ones here, I want to make sure that they're going to become less negative, so they're going to have less of a force on them. Now they're going to kind of come down on each other. Yeah, let me just make my head a little bit bigger. So if I'm out here and become less negative, they're just going to come in. It might still be a little bit negative, but gravity is going to take hold here. So it definitely looks like it's going to be A in this situation. What about they said B? Oh yeah, I crossed off A. Why did I do that? Okay, don't do that mistake. So I crossed off A. So remember I crossed these guys off already. So it's got to be B. Yeah, because I want to make sure they come down, and I want to make sure 2 doesn't change. What was I thinking? That's weird. Okay, so I'm just going to say glass, nothing happens. Charge distributes evenly. All right, so it's going to take some of the charge. Okay, so an experiment performed using an initial neutral sphere in a positively charged dome. Okay, so it's key that this was positively charged. Van de Graaff, that was that weird machine. Oh, it's right there. So that's positively charged. Oh, actually, let's just write that down here. So that's positively charged. Okay. The metal sphere, which is hanging on the thread, touches the dome and is repelled. So that means this guy now is positively charged because it touched it, right? Touches the dome. Okay, so that's positively charged. And the mass of the sphere is relatively large, 2.5 times 10 to the negative 5 kilograms. That's pretty big. The mass, or the picture showing what it looks like afterwards. It's reached equilibrium, so all the forces here are balancing each other out, which is nice. Okay, and then I got a little picture here. It looks nice. They kind of completed it for you. This is an equilibrium picture, so all these forces have the same, like all the x's add up to 0 and all the y's add up to 0. When it touches, it becomes positively charged. We already talked about this because it touched it. And the generator is positively charged. So the sphere becomes positively charged. I'll just cross that off because when you touch it, that's just the way it works in conduction. As a result of the transfer of electrons. Remember, electrons are the only thing that moves. Now I'm just going to go right here. Don't move. Okay. Magnitude electric force, and is that just the 2 questions? Yeah, next 2 questions. So we got to find out what this electric force is. So because we have this triangle, we can just use some trig here. So we can actually find the gravitational force, just going mass, which we know is up here. So 2 times 10 to the negative 5. I could take that and times by gravity, and I can find out what that gravitational force is. So 2e negative 5 here times the 9.81, and I get this 1.9662 times 10 to the negative 4 kilogram meters per second squared. I guess that's in Newton. Okay. I say 60, right? Yeah, 60. Okay, so we have one side of a right angle triangle, and we have an angle. So that means we could use any of the SOHCAHTOA rules. So right now what we have, here's the 78 down here. We have the opposite, we're looking for the adjacent. So we're going to use tan here. So I got the tan. We have the opposite, so I'm going to write that here. This is my opposite side. I'll just put newtons here. And we're looking for the adjacent, right? So this is OPP over adjacent. All right, so we're going to rearrange this for the FE down here. So do a little swap, 1.962 times 10 to the negative 4 newtons. And we're going to just divide this by tan 78. Now your answer's got to make sense too. That FE is much smaller. So you got to make sure that when you do the math, your number also ends up being smaller. And it does, because you went the wrong way, you get something larger. 4.17 times 10 to the negative 5 newtons. Okay, so let's see. Oh, okay, so I just have to write the numbers in here. So we got 4.17 And then we got a 5. C above. Okay. Okay, so one charged sphere or object has a, I said sphere, I don't know why. One charged object exerts a force of F on the second one. Okay, but Newton's third law said they're both going to be the same anyway. If the object distance is doubled and the charger one is also doubled, then the electric force that the one exerts in the other is, what is it now? All right, so we got to know what happens. So most people will say, oh, if one doubles and the other doubles, if you remember inverse law, one goes down, one goes up, and wouldn't they just balance each other out? But that's not going to be the case, right? So remember, Fe, or electric force here, is just going to be, let's just call it, it would be kq over r squared, but if we're doing proportionality, it would just be q over r squared, right? So if I want to find out what the new force is, and I change these numbers, so I double the q, but then I also double the r, but remember the r is inside the square, I'm going to get a really loud noise upstairs. So I'm going to have to double or square that 2, so I get a 4 on the bottom actually. It's a fourth of the force. 1 over 2 is a half, and then we have k, or q over r squared. Now remember, q over r squared is force, so that's what that is there, so I could just replace it with a force. So I got a half of my force. There you go. Cool. It's this question again. So it just kind of pops up everywhere. The angle of twist is going to measure the force. Let's just cross off that one. All right, because as these guys repel each other here, we're going to have Fe in both these directions here. And the Fe is going to cause the wire to twist around, right? So this is going to twist because of the Fe, right? So if it does that, get the force here. Okay, got some singing going on in the background here. Because the force is going to twist. Then we just have to kind of remember our laws here. So remember, Fe is proportional to q over r squared. Or, that's it. If you go q over r squared. So is it directly to the product of the charge on each sphere? Or is it, oh yeah, remember this QQ. Yeah, because now we have 2 charges here. Oh, I should probably go back up there. I forgot about that. So there's a Q here, and there's also a Q here. Oop. We only doubled one of the charges on this one, right? Yeah. There's 2 Qs. My bad, sorry about that. Otherwise it'd be an electric field. Okay, so it is directly proportional to the product because it's on the top, and then it's inversely because it's on the bottom to the r squared. So it's reciprocal to the, it's not reciprocal to the product. It's just directly proportional to the product. So because these are, oh, oops, sorry about that. Because these are on the top, oops, it's got to be that answer. Yeah. Actually, that's the only one that actually makes sense. You could just gone through these ones over here because they're all different. Figure out which one makes sense. Okay, yeah, so we got these 2 charges. You can see that the electric field is coming out of one and into the other. So that's my electric field there, right? So my electric field. So out of the positive into the negative. So that's how we define that. Now all these little dashed lines here are like the distances. So if you actually read through here, the dashed lines result from connecting the points on the plane that have the same electrical potential when a charge is placed in there. So if I put a charge here, instead it had an electrical potential of 5 volts down here, we'd also have electrical potential of 5 volts. And then maybe over here, this would have electrical potential of 2 volts, and then over here, this would have electrical potential of 2 volts. So the energies, if I put a charge anywhere along here, as long as the charges have the same magnitude, they'd have the same energy as well, right? So we can classify the fields as vectors for sure. So let's just cross out. I know fields are vectors because they have arrows on them. So cross off the scalar ones. because we talk about fields to start off with, right? The fields are vectors, right? Vectors. But these little dashed lines are kind of representing energy, right? They represent the potential, electrical potential voltage, which is energy in this situation, right? So, it's kind of like an energy, right? It's energy per charge, right? So it's energy. And energy is a scalar quantity, so it's got to be this one here. So, oh, geez, not going to be that one. It's got to be the one above it, right? The second time I did that, gotta make sure if I were to write the diploma, make sure I don't circle the wrong one by accident. So we have 14A. Okay. Cool. Okay, so which of the following best describes the relationship between electric field and the distance from the source? So they've done some line straightening techniques here, but we also know that they're not, like if I just put an R in the electric field here, it's going to be an inverse relationship. So it's going to look like this. And even if I square the R, it's still going to look like this, right? Because they are still inverses to each other. So if I want to straighten this graph out, I got to do that 1 over R squared stuff. So it's also just got to be C. You can remember the formula is proportional to Q over R squared. So technically, the slope of this line would probably be Q with a K in there. Okay, so we have a pair of parallel plates separated by 1 centimeter and a connected 12-volt battery. A magnitude of the field between two plates is E1. Okay, a second pair of plates separated by 3 centimeters and connected by a 6-volt battery instead. So it's half the voltage and 3 times the distance. Okay. Technically, I could just find the E's of both of these questions. I don't see what the... I just want to know how one compares to the other. So electrical field is just defined by the voltage divided by the distance between the two plates. So it's, let's say for E1, it's 12 over 1 centimeter. So if I wanted, I could put in 1 centimeter here. I'll put in meters though. So that's going to be a pretty big number. And then if I did it again, these other numbers, holy moly, I don't know what's happening over there. I get these ones as well. So here I'm dividing by a bigger number. So when I do that math, I get 200 volts per meter. And then if I do the other one, I'm going to get 1200. So I just compared the two. Like E, if I were to times E2 by 6, I can get this one up here. So E1 is 6 times larger than E2, but we're trying to go the other way though. So if I want to make sure they end up being the same, I'm going to have to do this one here. E1, if I times it by 1/6 of what it is right now, I can get E2. That's a weird question. Okay. Okay. We want to know the forces acting on in region Y here. So right here, what forces are acting on this charged sphere. It's negatively charged. Okay, that's key to this one. Because it's negatively charged, it's going to be attracted towards the top plate. So it's going to be a force, electric force going straight up there. So I'm going to cross off this one. I'm going to cross off this one. So I have a choice between those two. And we either assume that these are pretty far apart from each other, or if you remember some of our videos, the electric field is actually only really inside the two plates. So everything on the outside kind of cancels out a little bit. So there's really no field outside caused by these two plates. It's just the field that's inside that we're worried about. So it's going to be this one. Plus also if you looked at C, that FE is technically going the wrong way. It'd be attracted backwards, like it would be an A. Yeah. Oh, it's always gravity, right? Sometimes gravity is really small, so sometimes we just ignore it. There you go. In a Millikan type experiment, a sphere is suspended between two parallel plates here. So key word is it's being suspended. Okay. So that means there's got to be two forces on it. We got a force pulling up and a force pulling down. So because it has mass, you can see it's there. It's got gravity. So there must be something pulling up on it. But then remember that you can find out that Fe, the force, the electric force that's pulling up on it, by going E times Q. And they literally just had the field strength right here for us. So that's nice. So 20,000 newtons per coulomb. I only do this because it's easier in the calculator for me to type that out. Times the charge, which we don't know. We're trying to find that. I'll put a little question mark here. I'll just put Q. We're trying to find that. Here, this is mass times gravity. So what I know about these two things, they should balance each other out because they are suspended. All right. So that's straight back in there. Let's go E times Q. I got mass times gravity. I'm trying to find Q, so I go mass times gravity divided by E. Okay. So we got mass, 6 times 10 to the negative 15. You got gravity, 9.81 meters per second squared. I guess it's not accelerating, so we have to apply newtons per coulomb, newtons per kilogram, sorry. I'm going to divide it by 20,000 newtons per coulomb. Okay. Let's see what we have here. 6e negative 15 times 9.81 divided by the 20,000 number. So I get 2.94 times 10 to the negative 18. So it's got to be this one here. 2.94 times 10 to the negative 18, and coulombs. There you go. Kilogram meter per second squared. That's a Newton divided by Newton. Yeah, the Newtons cancel out. We're left with coulombs. Cool. Okay, so a positively charged object is sitting down at position M and then moves to position N in the region between these two opposite charged parts. Okay, so remember in these parallel plate systems, because there's so many charges in there, and when we do some complex math and stuff with all the K, Q, Q over R squared, the fields in here just goes from the positive to negative straight up. Okay, there's no kind of wiggly wobbly to it. Right? And the field is constant. All right? That's what we know. It doesn't have that R squared relationship, which is the single charge kind of moving out, because it's so many charges and because of complex calculations and adding together millions and millions of these charges together, everything just adds up to be the same. Because of that, if Fe is equal to E times Q, then this is also constant. Because charge is constant and the E is constant, so also constant. So it's not going to change, right? So it's not going to increase or decrease. Now potential, that's the energy. It's like me dropping an object. So if I drop this object, its energy is going to change as it moves towards what it wants, where it wants to be. Like this calculator up here wants to be down here. It has high gravitational potential energy. As it drops down, it loses its potential energy because it's going to where it wants to go. So here, same thing. This is going to speed up. It's going to gain kinetic energy, but it's going to lose potential at the same time. So gain kinetic, lose potential. That's that work energy theorem from the little chart back there. So I'm going to lose my potential energy because it's going to speed up, because it's accelerating towards the negative charge here. Okay. So it's going to decrease since EK increases. Yeah, I'm just going to put that in there. Okay. We got two oppositely charged plates that have an electrical potential of 120 volts here. They're 4.5 centimeters apart. There's an alpha particle that reaches in there. And it comes to rest just before, so I'm just going to highlight that. It comes to rest just before it reaches the other plate. So this is going to kind of come in here. It's going to go really, really fast and then slow down and then come back, and then it'll come accelerating backwards. But at the very, very top here, my VF is going to be 0. That's my speed, not my voltage. Right? going to have the highest voltage, actually, because it's going to be where it doesn't want to be. Okay, so we're trying to find out its initial speed down here, question mark. So we can use the change of energy stuff that we've been doing before. Like if I want to find out, because I know my final, if I use this formula, I can solve, if I can solve for my change of energy, remember change of energy is just final minus initial, and we're trying to find the initial, we know our final is 0, then I can just rearrange this formula to find that. So delta E times the Q. Remember, this is going to be final minus my initial, but the final is 0 because my VF is equal to 0. So let's assume this is EK, right? So I can find my EK initial by just doing this calculation over here. Okay, but we need, oh, we have the voltage, and we have the charge. Oh, cool. Now they gave us the distance. We could have used the distance in some other acceleration formula, but we don't need to do that. So we just have to go voltage times Q here. So our voltage is 120, I think, if I can get my head out of the way there. Yeah, 120. And our charge is an alpha particle. I think I mentioned that somewhere in here. Yeah, there it is right there. Let's highlight a different color. It's an alpha particle. That makes this positive 2 e's. So when you do your charge, it's 3.2 times 10 to the negative 19 coulombs. I think I made that mistake at one point when I did this before. So 3.2 times 10 to the negative 19 times 120. And it's a pretty small number, but because of the size of this particle, it's going to be a pretty fast speed here. That's equal to EK initial. And then I could just put 1/2 mv squared here. My initial speed there. Sorry about the number in the weird spot. So I can find my initial speed by going to the square root of 2 times this EK divided by mass. Yeah, there you go. So times by 2 divided by mass. So the mass of an alpha particle. So remember, this is an alpha particle. I'm going to write down some numbers down here that we might have needed. So this is 3.2 times 10 to the negative 19. The mass, gotta look around here, 6.65 times 10 to the negative 27 kilograms. Okay, so I have to divide by that number. Make sure to take the square root. 107, no, 107,000, that's right. So if I do the math over here, 107,466 meters per second, which corresponds to A here, 1.1 times 10 to the 5. Cool. Cool. Ah, we're about halfway done. Oh, we're an hour in. Okay, hopefully I can get this done here in 2 hours. Yeah. All right, so diagram 1 here shows the electric fields between 2 points. So you can see P is just going from north to south there. And then in diagram 2, it's the same electric field. Point P is in the same spot, but now we have a current carrying wire kind of going through there. So remember, vectors add together. So if I can figure out what the vector caused by the current carrying wire is, I can probably figure out how it's going to change. If they're going in the same direction, they get bigger. If they're going in opposite directions, they're going to get smaller. I also don't know whether or not this current carrying wire is going to produce a magnetic field that's larger or not. So it's probably not going to be A or B. Actually, it's probably just going to be D by process elimination, because if we don't know how big the field is, then how do we know if it's going to go left or right? It could get smaller, but maybe it's going to get bigger in the negative. I don't know. It's too complex. So let's just say it's D right now. I'm just going to get rid of that right there. But let's just use our hand rule and just double check. Okay, so we've got the current carrying wire, X is the electron flow, so I'm going to use my left hand. I'm going to go into the page, and my fingers are going to curl around, so I'm just going to plop my hand in there just a second. My fingers are going to curl around in that direction there. Yeah, everything's backwards, that's right. Okay, that does kind of work for you. So this is going to go counterclockwise here. Cool. So according to my hand rule, that's the direction of the magnetic field around this wire. But you notice at the top here is what we're worried about right here, that the field is going off to the left there. So it's going to add on to this one that's going on to the left here. So they're just going to get bigger. So they're going in the same direction. Right down here, hand rule. Okay. Yeah, so they're just going to add together. The alpha particle in a magnetic field travels in a circular path. What is the speed? Okay, so just remember that it's circular. That's one thing. So there's got to be FC in there somewhere. Remember, FC is an F net. So F net, what force is here? Magnetic force, nothing else. So just the magnetic force. There's probably gravity, but the magnetic force is probably going to be way more than that because the mass of the particle is really small. So I can use that formula. So let's go see. Magnetic force is going to be QVB. Again, we got an alpha particle. So this is going to be a Q of 3.2 times 10 to the negative 19. We got a mass of 6.65 times 10 to the negative 27. And then over here we got FE. FE is M. Oh no, not FE. That's an FC. It's a C there. That's going to be M times AC. M times V squared over R. That's what AC is. I'm just going to put some symbols there. There's supposed to be some absolute values there too. And we're just going to rearrange this for speed. So I got multiple speeds here, but remember that we can start dividing some speeds out because they're common on both sides. So one of the speeds cancels out. So I really just have V here. I'm going to times the R up and divide the M down here. So I've got all the numbers in here. So we got 20 centimeters, so 0.2 meters, times the Q, times the magnetic field, divided by my mass. All right, so plug all the numbers in there and see what we have. Oh, I think they're moving desks around. They have desks at the gym. I'm not using them all tomorrow because there's not that many kids writing physics. So it looks like we got 72,000. So 72,000 being answer A here. Cool. Okay. Current carrying wire is placed perpendicular to a magnetic field during the 20-second interval. Blah passes by this conductor. What's the average magnetic force on this in this case? So we got a wire, current carrying wire conductor, right? It's very specific length. It's this long, right? So this is going to be my FM is equal to ILB formula here. So we got a few things in here. So they gave us the magnetic field, which is great. All right, so they gave us the length at 4 centimeters here. They gave us the Tesla. It's a 6 number. I don't know why I wrote the zeros here and not the zeros there, but that's okay. But we need to find out what I is, and we're going to find this magnetic force. Now, I is Q over T. All right, that's on your formula sheet. That's right beside, it's right beside that formula actually. But we got to find the charge. And right now we know that's this many electrons, right? So if I know it's this many electrons, I just have to find the charge of that electron. I know the time is 20 seconds. So the charge of the electron is going to be whatever, how many there are, times the charge of an individual electron. All right, so I'm going to take that and times it by the charge of an individual electron. Oh, so it's going to be relatively a nice number here. Coulombs per electron, right? I'm going to divide this by 20 centimeters, or seconds, sorry, not centimeters. And then we can find out what the current is. So let's find out what the current is first. Okay, and then divide by 20. So I get 0.56 amperes here. And then I'm going to plug that back into this formula up here. All right. So I'm going to times it by this. Oops. I had a little brain fart there trying to figure out how to type numbers in my calculator for some reason. So I get 1.343. Yeah, that's right. 1.344 times 10 to the negative 3 amperes. So that's 1, 3, 4, and then I'll put a 3 in there for the exponent part of that. Okay. So we found that amperage, and then we put it back into that formula. It's an ugly question. It's an ugly question, but not impossible. Got to really think about it. Let's see, what kind of particle do we have? A high energy particle, accelerators, protons. Okay, so we got protons here. Just remember that a proton is positively charged. Technically, it's 1e, right? It's positively charged 1e. Close to the speed of light. Now it's traveling around at 7 tera electron volts, so a pretty big number. And we've got to make sure it's traveling around in the circle, so it's got to stay in this path. All right. So that means to keep in this path here, that means the force here has to be, the magnetic force actually has to be towards the middle of the circle to make sure this happens. All right, so I got to make sure that when I apply the proper hand rule, because we're trying to find out what the magnetic field is here, I got to make sure that force is going towards the center, and I'm going to use my right hand because it's a positively charged particle. So everything is going to line up. So I got my palm in this direction, my thumb in the direction of the particle, and then I notice my fingers are going into the page just based on the way the orient's here. So it's got to be C in this situation. Right, there we go. Just by setting up that hand rule, it's the only one that actually works. Okay, electrons or electromagnetic radiations, known as cyclotron radiation, is generated by these large accelerators. The radiation created from Maxwell's first prediction, accelerated charges, is created by the large electric current used to generate probably. Nope. It's from the change in the mass. Nope. By the proton as they move in a circular path of the accelerator. Yeah, because it's accelerating, right? It's a charged particle from the charge. And the change in the radius. No. No, it's because of the accelerated charge. And Maxwell's first prediction. You write that down. Accelerated charges produce EMR. Okay. The energy in joules, because up here they give it in electron volts, so this 7 tera electron volts, just converted simply into joules. I'm just going to take that tera, first of all, and get rid of it. So the tera is times 10 to the 12 electron volts. And I'm going to just times this by the 1.6 number to get rid of the electron volts. That's how many joules are in 1 electron volt. And pops out whatever number we need here. So let's see, 7 times 10 to the 12 times 1.6 times 10 to the negative 19. So negative 6. I guess I could have done the math in my head. I got that. Cool. So I'll just write this down. I don't see why I'd have to, but I cancel that. Okay, cool. All right, so it looks like we're moving on to optics here. So an object is 2 meters tall and located 7 meters in front of a concave mirror. So concave mirror, remember the focal length of that is positive. If it's convex, it would be negative, right? It has a focal length of 3 meters. So we know that the F is positive 3 meters The object is located 7 meters in front, so object is 7 meters in front. It's always positive, right? And the object height, which is 2 meters. So we want to know the size, so we want to know the object, or the image height. All right, so we want to know that. And what's the orientation? Is it inverted? Is it erect? So we kind of want to know the magnification as well. So to do all of this, I've got to have to find out what my di is. I've got to go 1 over f is equal to 1 over do plus 1 over di. Let's put in the numbers here. Yep, it's equal to 1 over 7 plus 1 over di. So 1 over di is equal to, so we're going to minus over the 1 over 7. Ends up being 4 over 21 as a fraction. It's a weird decimal, but we want to get di, so we've got to flip that over, right? You can go 1 over your answer, use the -1 exponent button there. You'll get 5.25 meters. Okay, it's a nice little positive number, right? Because it ended up being positive. Yep, this is actually a real image. It doesn't ask that question, but it's nice to know. But now we've got to figure out some other things, so let's use the magnification here. I guess if we find the height, let's just do that. If it's negative, it's just going to be inverted. Let's find the height. So we're going to use the negative di over do formula is equal to high over ho formula here. So negative 5.25 over 7. And on the other side, we have 2, and then we're just trying to find the hi here. Oh, it's going to be negative, so it's got to be inverted. Okay. We'll just times this 2 up, times by 2, divide by the 7, 1.5. So we get hi to be negative 1.5 meters. Inverted, like I said. If we found the m, we would have got a negative m as well. And then we could determine if it's diminished or not. And actually, we just look at it now. It's diminished. It used to be 2, now it's 1.5. Okay. Semi-transparent material. Well, this is, I remember these questions before. Oh, that's a different question here. Okay. You recognize a bunch of these questions. I use them a lot. Yeah. So, we just want to know where it's traveling the slowest. So remember the R or N value. The N value is a ratio comparing how fast it is compared to the actual speed of light, right? So the higher the value, the slower it's going, because if I take V divided by C, no, that's the wrong way, isn't it? C divided by V, that's the way I should do it. C divided by V. If I'm dividing by the slower number on the bottom, this is going to end up being bigger, right? So the slower it is, the bigger this number on the higher this number is. If this is going to go up, it means this has got to go down, right? So this would be the slowest one, being glass, because it's the highest N value. You can actually find those speeds if you want to. The angle of refraction. Okay, so I think if you remember doing this question, you can go through and find all these angles in here, like find for the water and then use the water to find the glass. But technically, kind of like that momentum question at the beginning of the test here, you can actually kind of ignore this stage here. Because what's going to happen, if you just kind of imagine that there was just a gap here, it's going to refract and then refract again and then refract over here. This middle step doesn't really matter. Mathematically, it just kind of disappears. You can just look at the ratios and say, this turns to this turns to this. Let's just ignore the middle. Yeah, actually, I'll write that down so you can see that, why you're allowed to just ignore it. So we got the top here. Let's call it A. So I'm going to write out the first little bit here. So this ratio, air over water, okay? Yeah, actually, do I want to write that down? No, it'd just be too confusing. Technically, you just skip one and go to the other. Just to ignore it. I was just trying to think of an easy way to show that you can technically. Yeah, I'm going to do it. I'm going to show you that you technically can ignore it. Okay, so theta, sine theta A over sine theta water. All right, so I'm going to do the water one. And then on the other side here, you got a N water. And the bottom here, you got Na. So remember, they switched there. And then on the other one, you have sine theta water over sine theta glass. Then over here, we have N glass over N, over N water. Okay, so what I'm going to do is I'm going to plug one into the other. All right, I'm going to show that if I were to put one of these into the others, a lot of things just start canceling out. So if I rearrange, say, this top one for NW and plug it into the one down here, so I'm going to get NW. Now this is a lot of work you don't necessarily have to do. But I'm going to show it anyway. I didn't want to take too long doing this, but times by NA, I'll put NA, and then plug it into this other one over here. You're going to get this. You're going to get sine theta W over sine G. And then on this side, we get NG over the bottom here, sine theta A sine W. And then we got NA here. Okay. And then what we can do is just kind of times this bottom piece up over to the other side, and these NWs are going to cancel out. So if I times that up now to the other side, I can get sine theta A over sine theta G is equal to NG over NA. And that's essentially just kind of ignoring the middle step where the water goes. Disappeared now. So if I plug it into there to find out what theta G is. So theta G, or sine theta G, is going to be, we're going to swap those, so we'll get N sine theta A times NA divided by NG. Okay, so I'm just going to type my numbers in now. Sine 36.8 divided by 1.5 times by 1. I didn't write that there. And then take the sine inverse of my answer. So 23.5. 23.5 degrees. Yeah, there we go. Yeah, it's a lot of work to show that you didn't need the water. Okay. So the next one here, light from the source passes through a prism, following the spectrum is absorbed. Okay, so some of these lines were absorbed by some gas, it looks like. Maybe by whatever's inside the container or the atmosphere. Depends on where the light came from. It separates because different wavelengths refract at different angles. That makes sense. I'm just looking at these different wavelengths diffract. No, it's a refraction because it's going through a prism. So it's not diffraction, so we'll cross that one off. I'll cross the diffraction here too. All right. There's no change in the frequency in refraction. It doesn't really describe why it does that. Yeah. It's all about the wavelengths essentially. Yeah. We'll go with that one. 28A. Yeah, I don't see it. Doesn't explain why, right? Doesn't explain why. Okay, there you go. The work function, blah. The maximum wavelength, blah. Okay, so remember that work function. I'm just got to write it up here. There's no space down here for some reason. Remember the work function is equal to HF naught. But remember, this is just energy, and this is just E, essentially. So I can just write down HC over lambda if I wanted to. So I don't have to find the frequency and then change it. I could just use this formula as is. If I rearrange that, I can get my lambda to be HC over my work. Now, because this is in joules, I got to make sure to use the 6.63 number. Oops. 34 number. I got the speed of light here. I'll just write that out. Oh, I'll make my head a bit smaller. There you go. Oh, come on. Oh, doesn't want to make my head smaller. There you go. 3 times 10 to the 8 meters per second here. And I'm going to use the joules. Negative 19 joules. Okay, so let's just plug those numbers in and see if it matches our answer sheet. So, no, it looks like it's going to be invisible. It's going to be in or it's in meters right now. So when I go through all this and I get this number, I get 2.563 times 10 to the negative 7. I don't know if it's going to ask this, but this is actually going to be 256 nanometers if we change it. So it's not within visible range. It's on the shorter end. So this is probably in the ultraviolet range. But what are we going to write down here? 2.567, because they want to leave it in meters. So we'll use that meter version. There you go. Which of the following equations represents the, so this is the conservation of energy rule, all right? So what goes into the photoelectric effect has to come out. So in the photoelectric effect, we've got photons coming in, right? They have very specific energy, the energy of the photon. We can find the energy of the photon by going H times F, right? So HF. And then if it hits an electron, what's going to happen is that electron is going to absorb all the energy. It's going to use a little bit of the energy to get out, and then whatever's left over is going to be the EK afterwards, right? So whatever is before, it's got to equal my after conservation of energy. So my photon energy has to be equal to the W plus whatever my EK happens to be. So if I put some of the formulas in, you notice they're using HFs here, and they use the V stop formula for the EK formula. So that here they want V stop is equal to, or EK is equal to V times Q here. They put a little E there for the electron, but that's fine. This is HF naught, and this is just HF, like I said up here. Now, which of these is the rearranged version for the, represents the relationship between stopping voltage and the threshold frequency? Well, it's probably either going to be A or B, because the other one doesn't have the threshold frequency and the stopping voltage are on the same side, so that doesn't help us determine the relationship. So it's got to be either A or B. If I try to rearrange this equation for V stop, let's just see what happens. So I'll subtract over the HF naught. Remember, this is a voltage, not a speed. The voltage required to stop the electron that's flying out here. Ooh, it's going to come to another plate over here. And then the last step here is divide the Q down. Yeah, so it looks like the formula that we have matches B. No, matches A. Why did I say B? I just have a habit of saying B. Cool. Yeah. A photon has a frequency of blah, struck the porous metal. It has a, what was it released and what's it? Oh, just 1 second.
1, 2, 3, 4.
Okay, I'm going to have to pause the video once in a while because they're bringing desks into my classroom here. But we want to find the work function. We have the kinetic energy. We have the frequency of the photon. This is just using that formula from just before there, like the energy of the photon, which we can find by going H times F, because we have the F here. Is equal to the W plus the EK, and we know the EK. They just gave it to us. It's right there. So I'm just going to leave EK there. So when I'm finding this energy of the photon, I'm just going to use the electron volt version, so the 4.14 number, and I'm going to rearrange this formula for W here. Okay, I'm going to pause right now. Okay, so I'm back. I've put some numbers here, you can see, but this ends up being 2.98 electron volts minus the 1 electron volt that we used to get out of the metal. So it looks like, or that the electron after it leaves the metal, so that's the kinetic energy, you're at 1.98 electron volts. So we get 30B. Cool. Okay, well, I remember doing this question before. Part of our, what do you call that, review at the end of the year there. So we're just trying to find which one matches the classical theory, which is usually the wrong one, and which one matches the quantum theory, which is probably the right one. But the quantum theory involves everything being packets of energy, like particles, and classical theory is all about waves. So let's see. Low intensity electromagnetic for a long time. So this is the key part. This is for a long time. Will eventually emit something, will cause photo emissions. Because of that, for a long time, that's going to be a classical theory, right? Because if it doesn't have the proper one, then it won't emit at all. Like red light's just not going to do anything for certain metals, but violet light will. So 2 would be our quantum theory, because it's unless it has a frequency that's higher, right? Unless it's frequency greater than the electromagnetic threshold frequency. So that's going to be a quantum theory. Electromagnetic radiation will increase if the intensity of the incident metal is increased. The energy of the electrons, if the intensity is increased. Intensity is about the number. That's not going to change. That's going to be independent, right? So that's going to be 4, and then the last one's going to be 3 here. So 1, 3, 2, 4, yeah. I guess you can switch some of the orders around. You can see on the answer key they did that. All the different combinations. Permutations, I should say. Yeah. Because of that independent part, I was going to think about what to highlight here. It's independent. It's quantum. All right. The nuclear atom was proposed by a consequence of the alpha particle scattering. This is Rutherford, right? So Rutherford, gold foil, right? Experiment. Oh, wait, gotta pause. All right, so we got those. Rutherford doing the gold foil experiment. So remember, we got the Dalton. We really didn't have an experiment, but he did the chemistry stuff, and then it goes J.J. Thomson with the cathode ray tubes, and then from J.J. Thomson went Rutherford, right, with his gold foil experiment. Then Bohr with his observations and Maxwell's theories put together. And then we got de Broglie after that, because we're trying to explain how Bohr's model works. Okay, so in the Bohr model, we got these energy shells that kind of explain the observation of emission absorption spectrums. So energy can only be released if an electron jumps from one shell to another, and the electrons can't exist between these shells. So in this question, we want to go from, it says here, from this one, he's going to drop all the way down to the third shell. All right. So that change in energy is what's going to be needed, because where that electron energy goes, it's got to go into a photon. So if I can find the change of energy, which would be final minus initial in this situation, so final minus my initial. So if I include the negatives, you'll see that, the change of energy is negative, which makes sense because the electron is losing the energy. So the electron is lost 3.4 electron volts. Now to figure out the frequency, use Planck's formula here, and we just had to use the proper H here. So we're going to use the H, that 4.14 number, to get the proper electron volts here. All right, and then let's just put that number in there properly. So we use electron volt one because we had electron volts here. All right, so let's use the proper one. And we get 8.2 times 10 to the 14 hertz. So it looks like the answer is supposed to be C in this situation. All right. Which of the following beta radiations will be deflected by a perpendicular electric field? Because the electric fields will affect charges. Gamma has no charge. It's just a photon, right? The only things that have a charge are going to be alpha and beta. So I'm going to cross off the gammas, and the only one left here would be A. All right. Which one's which here? So reaction number one, well, I guess it'd be considered fusion. You got two smaller things becoming a slightly bigger thing. So fusion. Fission would be one that's going from a bigger to a smaller. So yeah, I would say big to small. All right. So that's what fission is. All right. So it's got to be fusion for sure. All right. So it's got to be those two things. It's going from smaller things to a bigger thing. And, oh, this is the definition here. Since a large one makes a smaller one. No, because small nuclei make a larger one. Yeah, so that'd be A. Yeah. Cool. Which of the following statements describes 2, the left side of 2 compared to the total mass on the right side? Well, obviously not going to be the same here. It's releasing gamma radiation, and there's going to be all sorts of different kind of binding energy differences here. So they're definitely not going to be the same masses, right? The mass on the left is going to be smaller, right? So that's the left side versus the right side. So it's going to be, oh, what am I talking about? The mass on the right is going to be smaller because mass is lost, right? Mass is lost and converted to energy. So the left has more energy, then it changes down to smaller amounts of, or sorry, more mass, and has less mass on the other side. So where did it go? It became energy. All right. As electromagnetic radiation escapes from a super hot core, it passes through a cooler gas in the atmosphere. It results in an absorption spectrum. It's passing through the atmosphere. Gases that form this atmosphere. So these gases here. All right. So as it goes through there, it's going to absorb. I don't know what that's about. No, it's kind of related to that question. All right. To balance number 3, what do we need? To balance this equation number 3, we just have to make sure the numbers on the top and the bottom match up. So the bottom here, B has got to be 2 for sure because it's helium. All right, so this has got to be 2 and this has got to be 1. So that's just the definition of helium and hydrogen. So I know B is 2 and hydrogen is 1. Yep. All right. Then we just have to figure out what the other parts are. So are we producing, well, we got 2 of these. So the top number can't be 2 because then it's be creating helium-2. Helium-2 doesn't exist. You got to have at least a neutron. If you're going to have 2 protons side by side like that, you got to have at least some kind of other piece in there to make sure that they don't fly apart. So A has to be either 3 or 4, right? Because as it adds a 6 on the top over here, it's got to add a 6 on the top over here. So 4, 1, and 1. Yeah, it's going to be 4, 1, and 1. So a 4 and a 1 for that to work out. Everything's got to add up to 6. All right. 6, right? Yeah, 3 and 3. Yep, okay. Conservation of nucleons and conservation of charge, if you're looking at the chart back there. De Broglie hypothesized that these moving particles have a wavelength, and that's just the Compton formula kind of rearranged a little bit. P is equal to h over lambda. And we just have to figure out what the wavelength of a high moving electron is going to be. So remember, momentum is m times v, right? So that momentum there is that, right? So if I now we're just going to plug it in. We always use the Joule version for this formula. Okay, so negative 34. The mass of an electron, yep, so 9.11 times 10 to the negative 31. It seems weird. I haven't used that often in this form or this chapter. Okay, or this test. Type it all in there. Should get something relatively small. All right, so let's see what we have here. Divided by 9.11 e to the negative 31. Times 4e to the 8. Yeah, so we have B here. So 1.819 times 10 to the negative 9 meters. There you go, 1.8 nanometers. Yeah. Yeah, okay. So we got these two predictions of this diffraction gradient experiment. Remember this Dr. Quantum guy, where they shot these beam of electrons, maybe one at a time or a bunch of them at a time, through this double slit experiment. And what did they expect to happen, right? So if you were particles, like just like throwing balls through two different holes, you expect to see two different bands on one side, right? So this first part, this first graph here, is that particle-like one, right? And then the other graph, because of this weird wavy interference thing, that's going to be my wave-like. Right? So that's easy enough. Now, why are they doing that? Because they're interfering with each other. Right? Well, this is a poorly worded question, but I believe it's supposed to be. Well, they went with the diffraction part of it. The phenomenon they experience as they pass through. Oh, as they pass through. Okay. So the key word here, as they pass through. Not down near the end, because that's interference down there, but right when they pass through, they're going to diffract outwards, because they're waves, or they're acting as if they're waves. So 38 should be, I don't know why I circled those out. These are the right ones up here. 38 should be diffraction here. All right, oops. So as they pass through, right? Let me just put that as a different color here. As they pass through, diffraction. If it was much later on, it would be interference. We create this pattern, that would be an interference pattern. It's a very poorly worded question. I'm not happy with that one, but it ends up being A. The activity after 3 half-lives of this thing. So this one here, you can pretty much just kind of do without this graph, honestly. As long as you know where it starts, you just divide it by 3 2 times and you get your proper answer. So that's what a half-life happens. So I just divide by 2 3 times. It's like a half raised to the power of 3. So this is going to be 1/8 of what it was before. So even if I put 4,000 in there and divide it by 8, I get something approximately 500. All right, so I know the answer is going to be B. All right, this is 1/8 of what it was before. All right, so this is 1/8 of N naught. And it's a little bit more than that. It's actually, if we go by things here, there's 5 divisions, so it's 2, 4, yeah. So this is approximately 1/8 of 4,200, whatever counts per minute there. Do you get a better answer if we do it that way? Yeah, 525. Yeah, so we do it that way. So the closest one is 520. All right. So only a few more questions. Yay. The energy equivalence of 1 alpha particle. Well, that's a weird question. That's just E is equal to mc squared. We just have to know the mass of an alpha particle is 6.65 times 10 to the negative 27. And the speed of light, just that number squared. Okay, we want to be in joules here. So this will always just spit out joules anyway. Times the speed of light squared. So I get 5 point, and what do we got? We got 2, yep. Oh, it's going to be interesting. I want to write down what we have. 5.985 times 10 to the negative 10 joules. By the proper rounding, if I round this up, it's going to round up to 9. So I get 6.0 times 10 to the negative 10 joules. So 6010. Cool. Okay. There are 2 possible sequences. We did this decay chain before. So remember, beta negative is a negative 1 by the 0 on the top. If it was beta positive, it'd be a positive 1 on the bottom, but still 0 on the top. Remember, the 0 on the top represents there's 0 nucleons. The mass is really, really small, so you can't really consider it to be a nucleon. But the numbers on the top do have to balance out. So I have 212 here. If this is 0, that means the top number has to be 212 as well. And then the bottom numbers, the charge has to balance out too. So this is going to have to be 83 plus that negative 1. It's going to end up being that 82 there. So what is 83? I'm going to find out 83 is on my periodic table. Bismuth. So this is going to be bismuth here. Okay, so that's 1. Then bismuth is going to undergo either one of these two things. It's going to go alpha decay, so either going to have to go, oops, sorry. It's either going to go this way with a 4 and a 2. That's technically helium nucleus. All right. And then whatever's left over, so we got an 81, because we got to add up to 83. And the top is 208. That's the only other options we have. So 81, what's 81 here? That's thallium. So just TL here. So that's going to be 2. And if I go the other way, I got a negative 1, 0, beta, plus this other thing. So a negative 1 means it's going to be an 84. Is that an 84? Yeah, it's going to be an 84. And then top 212. 84 is polonium. All right, so that's going to be 3. And then either way, they should end up both being the same thing here. So I'm assuming it's going to be 4, but let's just double check with this one here. 4, 2, an alpha particle. The bottom number's got to add up, so it's 82 again. So it's going to be lead minus the 4 from the top. 208. Yeah, so we got lead this way. If I did it this way, got to end up being the same. So let's see, we've got bottom here, it's got to be 82, so that's good because that's lead again. Put lead there. And we don't change the top because you're taking away 0 from that 208 that was on this side. So check mark. Worked out. Okay. A neutron and a proton can be modeled by using quarks. So remember that a neutron has a charge of 0, proton has a charge of 1 elementary charge. So this got to work out. Doesn't say anything about anti stuff here, so I'm just going to cross off C and D because they're dealing with antiparticles. That's what the lines on the top mean. Antimatter. And same thing with this bottom one. Okay. So we just got to make sure it works. So an up, down, down, what does that end up being? So an up is a 2/3, and I'm going to add in a negative 1/3 and plus another negative 1/3. Well, that ends up being 0. So that's a neutron. All right, cool. And let's just see what an up, down ends up being. 2/3 plus 2/3 plus a negative 1/3. Ends up being 1 electron volt, technically. Or not electron, elementary charges. Yeah, so it's got to be A, 40A. Okay. Yay, we finished. Now, I did throw this extra question on here. There's a couple extra questions down here, but these are just the written responses from back in 2009 when they still had written responses. Back when I first started teaching. Yeah. Oh, a year afterwards, we still had that. Made things tricky. But the math of these are pretty much the same. So I can pause the video. You can just try to do these questions. Or you can try to do this one. You can just pause the video there and try to do that question too. But you can see how you can do it. Like this one here is going to be conservation of energy slash conservation of momentum. Probably do conservation of momentum here. And then this one here is just finding the net. Using those angles, finding the x and y's and adding x and y's. It says include free body diagrams and a bunch of other things. How do you determine the directions? Like these two negatives are repelling each other. These ones are repelling. They're all repelling each other, so they're all negative. If you want to try them out, you can. You can find the answer somewhere. I'm just going to stop here because it's about 1 minute and 38 seconds so far. So I'm going to stop this, and hopefully you had fun. Bye.